Well, good afternoon, everyone. Welcome to today's seminar. Today's seminar is special in that it's joint between EOL, M-Cubed, and Northwest Research Associates. So I'm going to hand it over to Dave Parsons from NWRA to introduce our speaker.
Hello, it's so nice to be back in this room at NCAR. So I wanted to just say it's my pleasure to introduce Kaustubh Mittal, who's a PhD student at the University of Reading within the Department of Meteorology. And it's also closely associated with the UK Met Office. Prior to receiving his PhD, Kaustubh completed his master's in ocean engineering and naval architecture at the Indian Institute of Technology, and then was debating where to get his PhD, and he wound up going to Reading and is quite happy there. And his bachelor's was in mechanical engineering. So welcome, Kaustubh.
Warm reception. Thank you, Sarah, for organizing everything. And so much thank you for NWRA to fund this trip, else I wouldn't be here. So this is a part of my PhD project. My PhD project is basically on forecast bursts. What are the mechanisms which drive forecast bursts? This is a part of that study. I'm Kaustubh Mittal. This project is supervised by Bob Plant and Sue Gray from the Department of Meteorology, University of Reading. Then I have a collaboration from the Met Office. My Met Office supervisor is David Flack. And then from NWRA, I have Dave Parsons as my US supervisor. So today I'm going to talk about the medium range European forecast bursts, their characteristics and their variability. Diving straight into the question, what is a forecast burst? Many of you wouldn't know this, but I'll try to define that. So forecast bursts have been defined as large errors in the prediction of atmospheric flow, especially in the medium range forecasting systems. So for contextual process, the illustration that you see on the slide is illustration of Rossby wave. These are eastward moving, slow moving planetary waves, and they are very important in defining the general atmospheric flow in a particular region, especially in the extra-tropics. By forecast error, what we mean is we mean the failure of a numerical weather prediction model. All types of forecasting model fail from time to time. We know that, be it a regional model or a global model. Some of the examples how this weather forecasting error can manifest. We are going to go through some of those. So here's an example of a regional model failure where the forecast failed to capture the convection. On these plots, you can see these plots are from the Met Office, and they show the two forecasts of the maximum column reflectivity for 27 hours and the 15 hours. That is shown in the panels D and E, and A shows the analysis of that. So if you compare this analysis with those forecasts, we see that there is an underestimation towards the eastern coast of the UK. We don't see much of a convection in both of these forecasts as compared to what the analysis shows. These are the short-range forecasts, as you can see from the lead times, which are very small, 27 hours and 15 hours forecast. The implications of these were actually the disrupted flight schedules during the holiday season in UK. So that was a big loss to the aviation industry around that period. So many of us have experienced such a small-scale convection when we travel by flights in the form of turbulence. So we know how important these type of forecasts are. Going forward, this is actually more intuitive to most of us. So these are the short-range to long-range forecasting in the extreme weather systems. So we know how difficult it is to predict an extreme weather, and it is worse if you don't predict them, right? So this here is satellite imagery of a windstorm, Polly, which devastated the parts of Netherlands in July 2023. As a forecaster, this was a nightmare. Ideally, you would want a public warning system to be activated around 7 days before, at least a week before this extreme event hits. This was very unpredictable kind of a windstorm, and it was really difficult to make that possible. So these extremes show the limit of our capabilities in terms of a forecaster, in terms of how you predict the weather. However, these extremes, they grab the headlines most of the times. However, the daily forms of weather forecasting are equally important. And by daily weather forecasting, I'll show you an example of it. But personally, there is something which I have realized when I moved from India to UK. Back home, the interest is in seasonal weather predictions. You would want to know the extremes of the weather. You would want to know when it will rain and when it will not, and that will be like sporadic, right? It will happen in monsoons and then it won't happen for, let's say, 2 months, right? So, but in the UK, the weather is the part of the daily conversation, and I found it in a very hard way. It changes every hour, so it's very important to check the daily forecast. But the most important part is to trust them. This here is an error in the 6-day forecast of a surface temperature field. You can see it's a forecast minus the analysis, and we see that there is a lots of error over the Netherlands and the Germany. So these temperature fields are valid on the 13th of March 2016. We can see the forecast is made on 7th of March, so a 6-day forecast. There is a widespread warm bias stretching across the Netherlands and Germany. While we experience this type of failure as a wrong temperature over surface, but it was actually the result of a model failing to predict the large-scale atmospheric flow during this time of the year. So bringing this discussion back to the forecast past, it's not just a missed extreme weather, but also it is an opportunity to create trust in the future stakeholders, basically the people and the lawmakers who need to make the policy decisions based on our forecasts. So a day-to-day forecast is extremely important. So whether it's an extreme windstorm or it is an incorrectly predicted Tuesday afternoon, these large drops in predictive skill, these specifically in the medium range, they represent a systematic failure in the model responses. So how do we measure that? To diagnose failures in the atmospheric flow, we look at the 500 geopotential height. The figure here shows a 6-day forecast of the Z500 field, which was valid on 13th of March. Over European region, so if this forecast, as you can see from the black contours here, if this forecast is accurate, this is what the actual truth also was. So looking at the actual truth, which is the red, the analysis, it diverges completely from what the forecast was here. So the deviation in these two fields can be quantified using some skill scores, such as the anomaly correlation coefficient or root mean square error. What they are, we'll discuss that in a bit. But in 2013, the study from Rodwell et al., they provided a definition to quantify such large errors in the Z500 field. And they quantified it based on these two skill scores, where they put a threshold over the ACC if a forecast which has an ACC which is below 40% and simultaneously the RMSE is above 60 meter, this forecast can be classified as a forecast bust. So for this particular forecast that you see on the screen, the ACC was 19% and RMSE was 144 meters. So typically this was a forecast bust. Interestingly, it is important to note that the surface temperature errors that I previously discussed in the last slide, they stemmed from this particular forecast bust over Europe. So upper level forecast bust resulting in a surface level error in the forecast. If you look at the historical capabilities of the European Center in forecasting these Z500 field, the progress is undeniable. This plot shows the average ACC from the 1980s to the current, with thick line showing the northern hemisphere capability and this thin line shows the southern hemisphere capability, and the y-axis shows the ACC values. So the better the ACC, the better the performance is. Lower the ACC, worse the performance. Expectedly, the shorter lead times, they show higher accuracy in forecast. We know that. But however, comparing the period from 2000 to the past 20 years, we see that the model has improved significantly, and that has been true in all the lead times. Largely, this progress has been driven by the model formulations, the better spatial resolution in the model, and also better usage of the observational data, as we see from the period of 2000 to 2008, when there was a improvement in the satellite observation, and better improvement in the data assimilation techniques. However, in the most recent decade, here the rise in the forecast skill has begun to level off. and that is true across all the lead times. The plateau is visible, and which brings us to a critical question that in this era of such advanced modeling, do severe forecast bursts still occur? Interestingly, if you ask this question in 2013, the context would still be the same because the improvements are incremental for every year. To solve this puzzle, the previous researchers have shifted their simple measuring averages across the systematic specific causes of uncertainty within a forecast. So, to understand why a model occasionally busts despite its maturity, you have to look at the two fundamental causes of uncertainty which are in the numerical weather prediction model. It is initial condition uncertainty or a model uncertainty. So at its core, a model needs two things to produce a forecast. An accurate snapshot of the current weather systems and the physical equations that move that current state to a future time. So an error in either of those components, maybe at the start or the process of that forecasting, will propagate into a wrong forecast. So the initial condition uncertainty, we'll talk about that for a little bit. These are a result of set of observational data and models' own short-range forecasts, which are assimilated together to produce an analysis which can be approximated as the truth of the current state. Literature and the operational experiences both have demonstrated a direct relationship between the better analysis and a better forecast. We'll see that with an example here. So on your screen, there is two forecasts which have been made from two different systems. So on the top is the ECMWF forecast made from the ECMWF system, and the bottom is the Met Office forecast made from the Met Office system. They both use their own analysis, and if we look at this particular region, we see large errors in the ECMWF forecast, especially towards the north and the south. However, those errors are actually lesser in the Met Office forecast. Now, if we flip the analysis, does this result remain the same? And it actually does. So if we use the Met Office analysis and make this forecast from the ECMWF system, and now if we compare those two regions, again, we see that the errors are comparable. Now, if we look at the ECMWF analysis and then use the Met Office forecast to make the same prediction, we see that the errors are actually comparable to what the ECMWF produced. So irrespective of what the model is, if the initial condition is better, the models tend to produce a better result. In terms of forecast bursts, we have looked into some of the case studies, and we have found that there is a presence of mesoscale convective systems near the forecast initialization time, which is a major source of uncertainty. So these systems are generally missed by nearly all the operation models, and sometimes these systems are powerful enough to perturb the upper level tropospheric flow. And those perturbations can rise and become a forecast burst over the 6-day over the region of Europe. Then there are other dynamic drivers as well. For example, a misrepresentation of warm conveyor belt. So around the extratropical cyclones, these are warm and moist ascending airstream. They can result in a large diabatic heating kind of an error in the initial condition. So they have tend to cause a certain forecast burst previously. And then finally, there is a case of transitioning cyclones from tropical to extratropical. It is a major source of initial condition uncertainty if a model fails to produce a correct forecast of these type of cyclones on their day zero. So looking at the specific case study is important in gaining the understanding about specific processes. However, is it systematic? What are those failures which systematically cause forecast bursts? So this study from Rodwell et al. In 2013 and Dillon and Parsons in 2017, they have used a composite set of burst cases and then tried to look what are the essential features which are present in the initial condition. So this here on the screen is one of the day zero forecast burst composites. So they used all the burst cases that they found from 1989 till 2011, and this here is the day zero initial condition of Z500 anomaly. And here there are two features which are very prominent. One is the trough around the western side of the US, which is Rocky Trough, and we have the northern part of the Canada where we have the ridge, which was known as the Canada High. And further investigation when they found that the Rocky's trough, the representation of Rocky's trough in the initial condition is an important factor in producing an uncertainty or not. And looking at the day 6, there is another very powerful feature that can be seen, which is the blocking towards the northern part of the Europe, as can be seen from the red dot over the left of the plot. Yeah, right of the plot. Yeah. So these are the Z500 anomaly composite at day 6 for all of these bust cases. So the misrepresentation of these rocky trough, this is a primary trigger for a decreased skill. This was mentioned in that study. Then this specific setup, what it does is it creates favorable conditions for small scale processes to occur, and those small scale processes can then induce perturbations because of the presence of these troughs. Now, while we have seen that what happens at starting day 0 is a very critical factor in producing in getting this information, whether the forecast will be a good forecast or bad forecast. However, it's just part of the story. There is another type of uncertainty, which is the model uncertainty, which is, if not as important, it is not less important as well. So essentially, a model's accuracy depends on how faithfully its numerical equations they tell you that story of physical flow moving from day 0 to day 6. These equations are limited. We know because of the constraints like resolution, and then those processes which are not resolved due to those resolutions, then we need to introduce the parameterization in those for those processes. Now, these parameterizations is basically a form of mathematical expressions which don't capture the full flavor of those small scale processes. So they introduce their own layer of uncertainty. Now, it is difficult to quantify exactly how much model physics contribute in the reduction of forecast bust. However, this example here might illustrate this point. So this plot from Rodwell et al. In 2013, they illustrated an attempt to isolate the model's role by tracking forecast bust across 2 different types of systems. The red line here shows the bust due to the operational IFS, which is constantly updated and with better physics and better resolution from 1990s to 2010. In fact, the resolution was constantly increased from 1989 when it was around 190 kilometers, and in 2011 the resolution has reduced to around 16 kilometers. So it was a drastic change. And then there is a blue line, which is a fixed cycle kind of a system, which was based on the IFS cycle of 2006, and then they produced a reforecast from 1989 to 2011. We see there is a downward trend in bust directly, which is very, very apparent in the red line. And this trend here is actually reduction in a bust on an average of around 3 busts per year, which is a lot. However, if you compare that with the fixed cycle busts, they have remained more or less the same, which shows that if the model doesn't improve, there are presence of inherent less predictable situations, atmospheric flow situations, which have been present since all throughout the whole period. But it is essentially the model improvement that might have driven this reduction in the forecast bust cases that we see. So yeah, bust remains constant in the model, which doesn't improve. So what we really want to say is that there is a clear evidence that that there is an evolution of model physics. It provides you with better numerical equations. They refine parameterization, and hence they directly result in an year-over-year reduction in the forecast bust. But at the same time, we also know that the inaccuracy in the initial conditions, they can also stem from the unresolved processes, and for example, the intense convections or the diabatic processes, and they can amplify those failures to become a large-scale failures. But what we don't know is how systematic is the loss of skill due to these kind of small-scale processes. Or what we don't know is how do bust actually relate to the kind of model physics that we want it to be. So by looking at those questions, our research framework is mostly driven by this particular question, that are forecast bust a chance event, or are they intrinsically linked to some inherently uncertain flow configurations, which is unavoidable for any of the models that we see. So for this, to answer this question, we go for two different kind of approaches. Firstly, we will quantify simultaneous occurrences of forecast bursts in different NWP models to account for the different physics, and then to see whether they are inherently linked to certain model physics, or are they, irrespective of what model show a burst, they are inherently present. And secondly, we would look at the characteristics and compare the type of bursts and compare how different models behave during such type of events. Now coming to the data set and the methodology, so yeah, as I mentioned, we are going to use different types of different models for this particular work. So we have used 4 global numerical weather prediction models: the European Center, the Met Office, NCEP, and the JMA. Just for an illustration, the resolution of all these models in 2009 is listed in the table, and as you can see in the 2023, all of the models have become better. The forecast period for our study, it starts from 2009, and the last forecast made was on 31st of December 2023. So it's a 6-day forecast. So the last forecast was valid on 6th of January 2024. So these are 6-day forecasts initialized at 00 and 1200 UTC. Diurnal forecast. All the operational data is regraded to 0.5 degrees to be for the data set to be consistent. The climatology we have used to calculate the ACC values, I'll discuss it in a few minutes. Those are used from the ERA5 reanalysis from 2001 to 2020. This whole data has been sourced from the Grand Global Ensemble Thorpex Interactive. It has all. Not only these 4 models, this data set has lots of different models from all across the globe. So yeah, it's a really exhaustive data set. So first, what is the anomaly correlation coefficient? Looking at this mathematical expression, there are 3 fields that are required from to calculate the ACC. One is the forecast field, which is the Z500F, and the analysis field and the climatology. So this this skill score is essentially a correlation between 2 anomaly fields, the forecast anomaly and the analysis anomaly. How good those correlations are is described by the correlation coefficient on the y-axis on this plot. The better the correlation, higher is the score. So anything which is below 40% is a forecast burst, as already defined earlier, and anything which is nearer to the 100% is definitely a good forecast. Now there is another middle part of this whole ACC space where there is ACC between 40% to 70%. All those forecasts which lie in there can be described as a poor forecast. Basically not a good forecast, but neither a forecast burst. Here on your screen, you can see the ACC time series. If you calculate the ACC for each of the forecasts that we have, such kind of time series can be made. And 7th of March 2016, the contour which we discussed in the first slide, it is marked here in the ACC time series. We see that there is a little bit of uncertainty right before that forecast was made, but the forecast was really good 12 hours later. So we calculated the ACC for all the 4 models from 2009 till 23, and this on your screen is the ACC distribution for all these 4 models. So if in any of those panels, the blue line shows the mean ACC, and the black line shows the percentage of shows the 40% ACC. Basically, anything which is below 40% ACC, all those forecasts were forecast burst. So looking at these distributions, it seems that all the models show similar kind of ACC distribution with a peak around 80 to 90%. On an average, the European Center had 82% ACC skill score of 6-day forecasts. The Met Office had around 80%, and NCEP and JMA had around 78 to 77%. So not much of a difference between these 4 models. However, if we compare the actual total number of bursts for each of the models, we see that there is a large difference. So the European Center has around 222 burst cases from 2009 till 2023. The same number for NCEP lies at around 400 bursts. So yeah, not a good picture for the NCEP. But what is interesting here is to see that the forecast bursts are essentially the tail event. They are not such regular occurrences, as we can see from the percentile values. European Center has just 2% of cases which were bursts. The same for NCEP is around 4%. So not much in terms of, so basically forecast bursts are an extreme kind of forecast events, not the extreme weather events, rather extreme forecast events. This here is the distribution of all these forecast bursts from on an year-to-year basis from 2009 to 23. The dotted lines show the trends, and the 4 lines basically show the progression for all the 4 models. The bars here show some of the data which is missing. It's just the representative of how many forecasts which are missing for each of the day. So the trend lines here, they take care of those 4 years where the data was missing and capture the trend overall. So if I just showed a plot from 1989 to 2011 where the forecast burst year-to-year occurrences were also captured. So from that plot, this is an extended burst period. So this is basically a climatology of forecast burst from 1989 to 2023. What is important here is to see that all the models show a decreasing trend. There is a difference between model to model comparison. So for example, for ECNWF shows 1 burst per year as compared to the NCEP, which shows 2 bursts per year. So basically the decline in NCEP is actually bigger than as compared to the ECNWF. One thing is interesting that the burst cases in 1989 till 2011, they showed a decrease of around 3 bursts per year. But right now, what we are seeing in this plot is a declining trend of just 1 burst per year in the European center. So that essentially says something about the leveling of the model's performance, that the models are not performing much better as they used to earlier. So like the performance of NWP models, the number of bursts have stabilized in the past few years, just looking at the European center. Now, if we look at the simultaneous occurrence of the burst in each of the models, we would like to understand that do these bursts occur in isolated in different models, or are they simultaneously occurring bursts? So the idea here is to understand if 2 models have a forecast burst at the same time, that points to a presence of some uncertain atmospheric flow situations. However, if these are isolated, that means that they are more intrinsic to the model's own behavior. So looking at these plot, any panel here shows the number of bursts for that own center, where the first bar shows the percentage of bursts which occur only in that model. The second bar shows the number of bursts which occur with any one of the other models, and the third bar shows the number of bursts which occur simultaneously with any 2 other models. So like that. The interesting thing here is to see that around 60% of bursts in NCEP and JMA, they are isolated events. So the question here arises, are they intrinsic to the model's behavior? The second interesting thing is that in ECNWF and Met Office, there are more than 50% of bursts which occur simultaneously with at least one other model, which is a positive sign actually. And thirdly, there is very small instance of bursts where all the models show the burst together. So even though we see the numbers not being very good in terms of the isolated bursts, however, we want to look at those numbers in a different perspective. So this here is an ACC time series of, and we can see that there is a dropout at the center. So these periods were burst periods. So this 10th of April 2011 case has been taken by Rodwell, and they showed that it's a mesoscale system kind of a burst, where presence of mesoscale system around the initial condition caused a burst 6 days later. What they didn't mention was why is there a period of uncertainty beside that 10th of April forecast. And we see that there is quite a lot of forecasts which were actually burst cases. So around 4 forecasts before 10th of April. Now, if we compare what Met Office, UK Met Office showed around the same time, we see that it didn't show any burst on 10th of April. Rather, it showed a decrease in skill before that 10th of April event. And especially on 10th of April, its forecast was actually good. So what it essentially shows is that the Met Office, it showed a burst, but it recovered much earlier than what the ECNWF shows. So just by considering this example here, was this ECNWF burst an isolated event? If you look at the NCEP, NCEP shows this bust in the similar manner as the Eastern WF shows a bust, but going further beyond the Eastern WF in terms of the minimum ACC score. And if you compare the GMA actually goes, it drops further and goes beyond than what both Eastern WF and the NCEP are showing. So this particular dot here, this forecast, is it a forecast bust which is isolated in GMA? What I argue is that this particular forecast bust occurred because of an uncertain situation which was present for throughout this period, and all the models show a drop, but each of the models own capability shows differently. So during this extended period of time when there was large scale uncertainty present, the Eastern WF showed 5 forecasts which were a bust. Met Office showed just only 2. NCEP and GMA, they showed 5 and 4. Moving away from this particular bust, there is another case that we can see from the similar time series. Here only NCEP is showing a bust case. However, around this point of time, we see all the models, they show a drop from their mean ACC score. So there are 2 conclusions that can be made from this. Firstly, the model shows a loss of skill during an extended period of time. So even though they don't agree with each other in terms of an instantaneous forecast bust, they agree with that extended period of time when they can drop their skill. And then secondly, there are periods when all the models, they show a decline, however they don't cross a bust threshold. So while we see the difference in the number of bursts in each of the models, simply identifying these failures after they have occurred is really not an objective for an operational forecaster. So in this context, ensembles form an important part of the discussion. So the question for a operational meteorologist would be that can they see whether a bust is coming or not? So to understand this, we in this study use the Eastern WF ensemble system as a representative system to look for the response during these three white cases. So what we have done is we have used Eastern WF ensemble for these 3 types of dates where one, only Eastern WF shows a bust. Second, when any other model shows a bust but not Eastern WF. And third, when no other model shows a bust. So what we have done is we have randomly selected around 350 dates when there was no bust in any of the model, and then we want to see whether there is a different type of a signature from the ensembles if in these 3 categories. The first approach would be to determine if the deterministic forecast it remains inside inside an ensemble. So what we want to do from here is to calculate the ACC of all the members and then compare the relative number of members which showed the bust. The second approach would be to look at the spread of the ensemble and to see whether that spread is representative of the uncertainty which is involved during these bust cases. So this here is the plot of all the ensemble distributions for these the 3 cases. I'll point out the 3 cases here. So this is the first category. First category is the no bust category. No model showed a bust. Second category when only Eastern WF showed a bust. Third category when any non-Eastern WF model showed a bust. So I have divided the third category into 3 parts when if it is a coinciding bust or if it is just a single center showing a bust. The ACC of all the ensemble members in each of these categories have been shown as a distribution in terms of box plots. The ensemble mean is shown in the red and the deterministic forecast is shown in the blue. And as you can see, in case of category 1, we don't have any deterministic forecast which is below 40%. That is by design. And the same thing you can see from the category 2 when all the deterministic forecasts are below 40%, again by design. So in category 1, this is what we want to look at. Firstly, we'll compare category 1 and category 2. So in category 1, no centers experience a bust. The ensemble members are tightly clustered. They have high ACC values for all of their members. As we can see from the box plot, it lies above 70% and has an average at around 80% mark. So this represents a high confidence, a high skill rate for all the members. However, if you compare that with category 2, you can see that there is a dramatic shift. The entire distribution drops significantly. With most of the members which they fall below 40% mark. The ensemble mean, it lies between 40% to 70% mark. Now, if we look at the category 2 versus category 3, so in category 3, we are looking at the cases where non-Eastern WF bust, non-Eastern WF model showed busts. So the ensemble distribution here is still clustered as compared to the category 2. However, not as tightly as we saw in the category 1. The general ensemble mean, it lies above the deterministic forecast. The general ensemble mean, it lies above the 70% mark. However, there are distributions where the ensemble mean is also below the 40% mark. So it shows a amount of type of uncertainty which is present in the category 3. Now, if you compare the category 3 with category 1, the contrast is big. The ensemble is a reliable cloud with high accuracy members in the category 1. However, in category 3, the ensemble can exhibit a large spread. Some members even reaching negative ACC scores. So there is a decrease in number of ensemble members which are above 70%. Now, looking at the spread error relationship, this will show us something else. A reliable forecast system should be able to foresee that unpredictable situations. So that can be defined with the increase in spread. So that increase in spread should also come out to be with the increase in error. So what we want is that in that spread and RMSE kind of a scatter plot, every member should lie on that diagonal line. So in this scatter plot, we compare the ensemble spread against the actual forecasting error for all these 3 categories. The cases are clustered more tightly along the diagonal 1:1 line in the red. The red are the non-bust cases. So we see higher the spread, higher the error, lower the spread, lower the error. But if you look at the blue plots, which are the Eastern WF bust, we see that the spread is actually less than the error. So the ensemble system behaves overconfidently around these bust cases. It doesn't provide much of the information to the forecaster because the spread is not as large as we want it to be. If you see the same structure in the green, which is fascinating. So this green is the non-Eastern WF bust, basically bust in any other model, not the European center. And we still see that those the spread is actually still not representative of the error which is produced in those kind of ensembles. The RMSE is generally greater than the spread in those green dots, which the conclusion from this can be made as the ensemble really don't show the spread during the bust cases. So for a forecast system to be truly reliable, we need it to move those blue and green outliers closer to the diagonal, either by improving the model physics or to reduce error, or by increasing the spread to better reflect the true uncertainty in the atmosphere. Now, we are going to move from the instantaneous forecast bust to a more spreaded kind of a forecast bust, which is known as the forecast bust episode. Before that, a few points that I want to reiterate. Firstly, that during non-Eastern WF bust, we see that the Eastern WF ensemble, it exhibits the overconfident behavior. It is the forecasts are not really confident in terms of their spread and error skill score. Unlike no bust scenario, the cases here, they show significant decline in the number of members which are above 70% ACC. More number of members are between the 40 to 70% ACC range, indicating a presence of uncertainty. The occurrence of bust, regardless of which model we use, it does indicate a presence of uncertainty. So therefore, a forecast bust should not be viewed as an isolated instantaneous failure. Instead, we will see how an extended period of low predictability would help us in actually determining the characteristics of each of the model. So what we do is we define different spaces in this ACC versus time series, where anything on the A section is a drop period and anything after A is a recovery period. And these two periods are marked by the minimum ACC. So during a forecast bust, we do have a minimum ACC score. So anything before that minimum ACC score, we can say that the model is still dropping the skill. And anything after that minimum ACC score, we can say that the model has started to recover. So this drop and the recovery are measured against the poor forecast threshold, which is our 70% threshold. And minimum ACC is basically any ACC which is below the forecast bust threshold, which is the 40% ACC. So this whole period can be isolated by saying that there is a definitive start and definitive end. And by definitive, I mean there should be 3 good forecasts before the model start to drop their skill, and there should be 3 good forecasts after the model has recovered, to say that the recovery has been final and to say that the drop has finally started. So since we define our forecast burst episodes like this, there are certain mathematical characteristics that we can straight away derive from this kind of architecture. Firstly, we can define the duration. We can say that what is the duration of burst. We can also say what is the minimum ACC score during a certain burst episode. We can say what was the drop rate, how fast the model dropped the skill, and we can say how fast the model recovered. So apart from that, there is another metrics that we can calculate from here, which is the total duration. Basically, the time when the model started to drop skill below the poor forecast threshold, and the time when it reached the poor forecast threshold finally. So by doing this, if we actually look at one of the actual ACC time series, we can say that these are number of instantaneous forecast bursts which occurred together. However, if we use this algorithm, we will say that these are 4 instantaneous bursts, but only 1 forecast burst episode. So this forecast burst episode encapsulates all the uncertainty around this period of time, and then we can actually calculate, we can actually compare the response from each of the 4 models. As an example, this is an ECMWF forecast burst episode showing all the forecast burst episodes that we calculated. So out of the 222 instantaneous bursts, ECMWF showed around 107 forecast burst episodes. These gray lines in the plot show all of those ACC time series, which show all those 107 poor forecast episodes. And if we overlay each of those time series over their minimum ACC, as can be seen from the 0 time step on the x-axis. So anything before 0 is a drop, and anything after 0 is a recovery. These time steps are bifurcated in 12 hours because that's how we have used our data set of 12-hourly forecasts. And this black line is the average line, averaged between all these gray lines along the ACC y-axis. So this average line here actually shows the average performance of the European Center around any type of burst. So in terms of numbers, what do they show? So 107 poor forecast episodes for ECMWF. The duration of these episodes was on an average around 27 hours. The total duration, basically starting from the poor forecast, ending to the poor forecast, is 85 hours. The minimum ACC on an average reached was around 23%. The drop rate and the recovery rate was 26% per 12 hours to 31% per 12 hours. Now, putting these numbers in the context, what do these numbers actually mean? We can look at all the 4 models. This is the profile for all the 4 models. And there's not much of a difference that we can see from the profiles, but these numbers actually are significantly different in some ways. Firstly, the number of burst episodes. So if you remember, the NCEP showed around 400 instantaneous bursts, and now we see only 170 burst episodes. What does it mean? So it means that all those 400 poor forecasts, they were actually so close together that those were more like uncertain periods rather than different instantaneous forecast bursts. So here in ECMWF shows the least number of burst episodes as compared to the NCEP, which is the highest. Now, looking at the minimum ACC, we see that the GMA has the lowest average minimum ACC during these burst cases and the longest burst duration. The burst duration is, and if we compare that burst duration of JMA, which is 44 hours, to the Met Office, which is the 26 hours, it is the shortest. And this difference is actually statistically significant. For NCEP, the peculiar feature is the asymmetricity. So the drop rate of the NCEP is lowest, is actually comparable to the JMA, but its recovery is very, very fast. It recovers, in some of the burst cases, it actually recovers faster than the Met Office. So each model, it shows a different type of skill progression on an average, and that might show the dependence on model physics and different type of initial conditions that each of the models use. The second part is to look at the seasonal trend. So we know that the bursts occur throughout the year, but from the seasonal trend, we can see that there is a varying frequency of bursts occurring in each of the different months. This plot here shows number of bursts per month. The 4 lines show the 4 models, and again the bars here show the number of data which is missing. It's the same number of data that we saw in the year-to-year plot. We see that there are a large number of bursts in April to June cases as compared to a very, very big drop in July, and then again the number of bursts picking up in the autumn season. So There are different mechanisms which might be possible for burst, especially looking at the study from Lillo and Parsons in 2017. They suggested, looking at this seasonality in the burst occurrences, they suggested that there might be different types of burst signatures around different seasons. For example, in the summer, there might be high MCS activity over US that might be causing the burst, as against in autumn, where there might be more tropical to extratropical transition of cyclones, because that is the period of high cyclone activity in the Western Atlantic. And then we have the burst in winter, where might be more cyclogenesis over the southeastern part of the USA, which might be the cause of more burst in the winter. Now, if we take the season as a proxy of different type of mechanism, we can actually look up look up to the different response that each of the season can provide into the burst characteristics. So what we did was we took all the burst episodes for all the models, put them together, and bifurcated them with respect to the seasons. And this is the seasonal profile that we get. This is actually more similar looking than what we see from the model to model comparison. The few of the things that I want to highlight here is the difference between the winter and the summer bursts, where the winter and summer months, they exhibit significantly contrasting burst characteristics, ranging from the burst duration to the average minimum ACC that was reached. The autumn and spring months, they show similar kind of burst periods. Even the numbers are similar, and the burst characteristics are also similar. So this is the current work that we have done, and I'm currently compiling them in a paper. The next piece of work that we want to do is to see, does this presence of specific precursor events, such as the MCSs or the extratropical cyclone transitions, do they consistently act as a trigger for this medium range forecast burst? And if they do, what are the what is the variation in the model response during these kind of burst during these type of burst mechanisms? So currently what I'm doing is to look at the initial conditions and then seeing what are the features which are present. So this here on your screen shows for all the 222 European center bursts. The top plot shows the Z500 anomaly for the initial condition, and the bottom plot shows the Cape anomaly, the convective available potential energy around those burst conditions. So these are all day zero initial conditions, and we can see that there is a low around the western part of the US in the Z500, and also we can see that there is a high Cape present around the southeastern part of the US. So these blocks that I've mentioned, what I wanted to do was to see how significant they are, how systematic they are. So averaging these Z500 anomalies in that box, and simultaneously averaging the Cape anomaly in this box, I plotted the scatter plot of all the ACC values which are there. So this plot here is the Z500 anomaly averaged over that block, the Rockies block. And what we can see is there is approximately 50% chance of a negative Z500 anomaly, as also the positive Z500 anomaly. What we really wanted was to see a systematic trend in the negative Z500 anomaly as compared to the ACC. But we see that there are the number of forecast bursts are similar in the negative as well as the positive part. The second thing that we did was to compare the Cape using the same methodology, and here it is. The results are actually not that systematic. We see that number of bursts in the left-hand side of the column. The left-hand side of the column shows the number of bursts, and we see that they are not really related to the high Cape anomaly that we wanted to see. High Cape anomaly is actually more. It shows more forecast with better ACC values in the right-hand side. So high Cape anomaly doesn't result in a reduction of the skill score. So the next step for us would be to look into the observed MCS tracks and to see how they interact with the Z500 lows and the ridges over the eastern part of the US. So in conclusion, what I really want to say in the summary is to say that while continuous improvements in model physics have significantly reduced the frequency of failures, the forecast bursts have still remained an inherent challenge for each of the models. Secondly, the bursts are not really the random anomalies, but rather the presence of uncertainty seems systematic by looking at the ensembles. then we can see that the forecast burst is accompanied by a drop in forecast scale before the instantaneous forecast, and then there is they are also marked by a recovery. So it's basically more of a extended period of uncertainty rather than just the instantaneous episodes of forecast bursts. And then what we want to say is that the numerical weather prediction models, each of the models show distinct type of behavior during a certain forecast burst, and these episodes have different characteristics for different seasons as well. So what we really want to say finally in the second piece of the work is how this distinct behavior related to the certain atmospheric flow conditions. So with that, I close my talk. Thank you so much for listening. Thank you.
Thanks, Kaustubh, for that thorough analysis. For those online, you can enter your questions in Slido. There will be a tab above the video screen. While they're getting those in, do we have any questions in the room?
Thank you so much. This is really great to see all this very comprehensive statistical understanding from the all different models, ensembles, and then the burst frequency. So my question is, it's good to see them from the day 6 time series of ACC. Do we have a sense of how these burst event era, are they wrong from the initialization, or they just grow linearly or non-linearly through day 1, day 2, day 3 to day 6?
Yeah, so there have been some studies which have looked into some of the case studies and looked at how these errors have propagated from day 1 to day 2 to day 3 and finally to day 6. In some of the cases, you can see the errors building up at around day 3 and then propagating towards the European region and then finally blowing up to become a forecast burst. In some of the cases, you can see other errors actually being generated around day 2 itself, and you see those large errors and then you see how they propagate towards the day 6. So that is essentially not a scope of this study, but there have been case studies which have looked into this.
Okay, thank you.
Hey, great talk. I wanted to ask about the maybe very final set of plots regarding future work. Kind of curious regarding the, and I understand this is ongoing work, but I'm curious about the approach for just really focusing on, for example, these high CAPE environments, because you showed these statistical plots for the ECMW, or for the various model busts, like there was sometimes a maxima in the almost springtime period where you expect these maybe more synoptically forced type of MCS environments, which aren't necessarily always consistently going to be high CAPE environments. And I think even in your plot, you showed that there isn't whilst there is a high CAPE environment oftentimes during these busts, I believe you showed some stifling, which I assume was for statistical significance. Yeah, I didn't really see a lot of stifling actually over much of the CONUS region. There was high CAPE, which implies, these are maybe some environments conducive to convective storms. But yeah, I feel like that's already a somewhat first guess telling you that CAPE might not necessarily be that important. And so maybe as a recommendation, whilst you're working at Reading and with David, my suggestion would be, because you talked at the start about these potential issues with model physics, and I think especially if you're looking at MCSs, I'd be curious to, my thought is like maybe in these environments that exhibit really rapid upscaling of kind of atmospheric motion, so something that can like really force kind of very vigorous and like really rapid scale interactions, these kind of really rapid upscaling processes. And so for that, I can see that MCSs might be important here. You have this kind of nice, CAPE composite, but my thinking is more, would it be interesting to look at, say, processes that might be more favorable for rapid upscaling, like looking at regions of strong vertical shear. So maybe vertical shear, I'd recommend that as a kind of maybe an ingredient to focus on more, just because it's not very well it's not very well forecasted still in physics-based models, and it's a mechanism that can at least enable upscaling, because CAPE itself isn't really a mechanism to enable upscaling. It'll just tell you that you might have a good chance of convection, but it's really that vertical shear that might be really worth focusing on, because at least that is an example of a mechanism that's going to lead to vigorous upscaling. Might be pretty complicated for the model to resolve, but that's a suggestion. Sorry for this is not even a question. So sorry, but great presentation. I don't know if you have any other thoughts about any additional kind of things to like focus on more.
Firstly, I agree with your comment. CAPE is, while we have looked into CAPE, we really find that it's not really an indicator to sense the presence of a mesoscale convective system occurring around across that region. So yeah, I agree with your comment there. I think the further approach that we want to see is also to look at the larger scale flows and to see how they develop from day 0 to day 6. So one of the approaches that I am currently looking into is tracking the trough and the ridge axis, and to see how frequent they are around the burst cases, and if not, then what are the locations which are more suitable for them to be there, right? So that kind of a thing. So yeah, thank you for the comment.
Great, thanks.
You very good talk. You attributed the improvement at the beginning of the drop of burst over time. You attributed those to the model improvement. But as you know, observation has not been standing constant, right? I mean, from 2009 to 2023, I'm sure the number of observations available for those model initialization have changed significantly. And so what do you think is the role in changing observations?
So I would say that changing of observations would definitely provide you better analysis, and definitely better analysis will provide you with better forecasts. However, when we saw that trend in the last 10 years in terms of the improvement of the model, we don't see much of an improvement now in any of the lead times. So that might suggest that even though the initial conditions might have improved for the models, it might show a little bit more into the model physics, whether a particular type of model is suitable enough to forecast in that kind of a situation or not. I don't know if it makes sense, but that's what the main objective here is in going into the second piece of work, to effectively quantify that for this particular type of situation, is there a relationship with the model physics, or is it more a relationship with the actual initial conditions that the models produce? So yeah.
Okay.
Thank you. Great talk. So my impression is that your focus was over the mid-latitudes, so Europe and US. So did you get a chance to look into the tropics, for example?
So
I'm sure there is forecast bursts.
Definitely.
So do we have like any quantitative information or statistics?
So I have spoken to a few people regarding the burst cases in the tropics. Firstly, this definition, I don't think this definition would be very useful for the tropics. Secondly, it's difficult to find the analysis, the comprehensive analysis. So there might be case studies which should be working on the tropical meteorology, tropical weather forecasting, but I don't see a comprehensive study based on this particular definition. So this definition, I would say, more suitable for the extra-tropics, where the flow is more important in terms of the Z500 and those kind of flow situations. Yeah.
Questions? Well, that wraps up our hour. Was there another pressing question? All right, go ahead, Sebastian, if it's quick.
Quick speculation. We're currently seeing that fewer and fewer radio sondes are being launched in the US. Could you imagine that the UK would sponsor some radiosonde launches in the Midwest or where the Canada High is to improve the forecasts in the UK?
I'm pretty sure they do. But let's say I come up with a nice little hypothesis saying that the NCEP model might improve by the use of radiosondes, then definitely yes.
Nice question, Sebastian. All right. Well, if there's any more pressing questions, Kaustubh is in town until Friday. Let's thank him one more time.